Thank you, and yeah, also thank you to the organizer for inviting me. So yeah, this is going to be a fairly this is something I've been working on for a while now, and yeah, it's the perturbed Kepler problem and the spherical midpoint method. It's just the spherical midpoint method is of course due to class and co-authors, and there we are. Okay, sorry, the clicker is not that welcome. Okay, yeah. So yeah, this is what I'm going to talk about. It's the perturbed Kepler problem, and I'm going to talk about the Poisson mechanics, a bit about Poisson mechanics. We've already seen that. We've already seen that before in this at this conference, and I'm going to talk about something called average mechanics, and finally I'm going to talk about how you can do symplectic integration of the resulting differential equations. And yeah, these are sort of antecedents where all of this is coming from, and we talked about all this at the breakfast as well. The original Kepler problem is, of course, Kepler discovered that the planets are moving on ellipses, and Newton showed that this is the solutions of certain differential equations. And in the 30s, Fock and Bergman, they were looking at the quantum Kepler problem, also known as the hydrogen atom, and then they have a Poisson structure of the various the Poisson structure of the first integrals of this Kepler orbits. And they have a Poisson structure, and that was in the 30s. The method of averaging mechanics that I'm going to cover into is, well, Krylov and Bogolyubov is often credited with it, but there's a lot of other ideas, like Einstein did it already for the orbit of Mercury, and there are a lot of other people who have sort of independently covered this in various ways. And finally, the spherical midpoint method, which is a geometric integrator for it's a geometric integrator for the Poisson manifold discovered by that Fock and Bergman described. So that's why. So that's how all of this joins together. And yeah, so this is the Kepler problem. It's a Hamiltonian. So it's a Hamiltonian system described by this Hamiltonian, and as showed by Newton, this is solved. The solutions of these, the position is always going to move along this ellipsis, and there is something about you need to figure out where you are on each ellipse for each time if you want to describe the solution exactly. There is some nonlinear equation you have to solve, but this is the solution. It's always moving along this closed ellipsis. Now let's see. Now I wanted to show this GIF, and so it's a Hamiltonian system. And we know that, can I make this bigger? I don't know. Okay, I'm not that good with graphics, so this is just something that I've tossed together. This is something I made yesterday, actually. So this shows you what happened now. I've taken the Kepler system and I apply a symplectic method to it. From geometric integration, we say that if you have a Hamiltonian system, you should always use some kind of symplectic integrator. So this is the midpoint method. And as you can see, it's not quite following the ellipsis. It's going to slowly rotate the orientation of the ellipse. So what's going on there? So it's not perfectly captured. Of course, this structure is not perfectly captured by symplectic methods. But on the other hand, we know the solution exactly. So why are we bothering about applying numerical methods to it at all? So, well, okay. So the reason we could be interested in applying the numerical methods to it is that the Kepler problem is not exactly the real world. You see, for instance, for a planet such as the Earth, there is going to be some corrections to this the Kepler Hamiltonian. For instance, so this is the dominant one for Earth, low Earth satellites. It is due to the Earth not being a sphere, it's being slightly oblate. So there is this, so that means that there is an extra term here. This is some spherical harmonic, and there is this divided by the r cubed. And then we see here J2 is called the dynamic oblateness of the Earth, and the dynamic oblateness for Earth is about 10 to the minus 3. So you have your Kepler, you have your Kepler Hamiltonian, and you have some small parameter times a new term. So and yeah, it's a perturbed. So this is the perturbed Kepler. Perturbed Kepler. You could have something else there representing some other kind of correction for. To correct for relativity or for the moon or something like that. And effectively, it's going to be a multiscale dynamical system. The satellite, that's my image here, is that I have a satellite orbiting Earth, and it's going to trace out these ellipses, but which ellipsis traces out is slowly changing over time due to this perturbation. And yeah, and we actually know the fast dynamics, so we know how to solve this exactly. So you could say the idea here was and there are several ways to approach it. The idea is sort of I want to compute this, I know how to compute this exactly, and then I want to use those exact solutions when I'm solving the whole entire system. So fast dynamics would be what's happening here? Actually, the classical midpoint is actually also a good illustration of how these orbits will look like. This is a different perturbation. This is this different perturbation. It's the perturbation from the modified Hamiltonian. But yeah, they're almost tracing out the ellipse, but which ellipse is changing over time. And by fast dynamics, I mean moving along the ellipse. Okay, let's see. Let's go back. Right. Okay. And the idea here is the idea that there are probably several ways you can do it. The idea I've been looking at is the method of averaging. So and I think it's easiest to explain the method of averaging using the language of Poisson mechanics. So these are, a lot of you probably know that when you have a Hamiltonian system, you can also write it as a Poisson system using for the canonical Hamiltonian systems, you have the canonical Poisson, where you describe this bracket. It's a Lie algebra structure on the set of functions. It looks like this with partial derivatives, and then you say that for any function f, the derivative of f along the orbit of your system is going to be given by this bracket. That's Poisson mechanics. So you always describe the evolution of the system by how functions evaluated along the path change with time, and it's given by this bracket. So that's canonical Poisson, but yeah, you can describe this more general, and yeah, these are the rules. You need some smooth manifold, and you have a bracket which is going to be it's a Lie algebra, and you also have this Leibniz rule that it acts as a derivation on its arguments. So, and the example that we always pull out in addition to the canonical Poisson is, well, if you have R3, then you can do the bracket looking like this. You just take this vector triple product between your position and the gradient of your two functions. And yeah, you can check that all of this works. And this is, of course, the class was talking about Lie Poisson brackets. And this is the Lie Poisson for SO3 star. Okay. Yeah, so when we're doing mechanics on this, there are a couple of things we need to care about. and that is so whenever you have this Poisson bracket, if you have a Hamiltonian, then this is going to define some kind of vector field in the way that I showed earlier. You also have the Casimir functions. They occur in these. They occur here. So those are the it's called the center of the Lie algebra. So you will have some function which are just killed by this bracket. You have functions that are non-zero, but that this bracket always tends to 0. So they will arise from the Poisson structure, and if you look at all the Casimirs, it's of course an infinite set of functions, but they're always going to be generated by some low number, and then some finite number, and then you look at if you have a level set of if you have a submanifold that's a level set of all Casimirs, then that's going to be exactly a symplectic manifold. Yes? Well, no, yeah, no. Well, I said the level set. If you have a level set of all Casimirs, then you have symplectic manifolds. Oh, okay. So maybe the other direction isn't true. No, it's not equivalent. But yeah, okay. Yeah. Okay, fine. Yeah, no. It works. It works one way. This implication. So yeah, again, this example with R3, the Casimirs are just going to be, say, they have a function of the norm. These are all the Casimirs are going to be described as this. By this in this case, and the symplectic leaves are spheres with center 0, and there's some singularity going on when you have at the origin, but let's kind of ignoring that for now. Yeah, you see here if you put this in, C of z equals the norm of z square. Then if I plug that into the bracket, I'm going to get the vector triple product with z and the gradient of c, which is going to be proportional to z. And you plug it into this triple product, you're going to get 0. Okay. So let's return now to the perturbed Kepler problem, or in general perturbed Hamiltonian systems. And for simplicity, I get rid of all these physical constants. So I'm setting the mass of my satellite to 1. Mu is the strength of the Earth's gravitational field. I put that equal to 1, and alpha is now the radius of the Earth, or the mean radius of the Earth, I guess. So we have this, and this J2 I'm calling epsilon because it's a small parameter. So, okay. So the idea for average mechanics, the way I understand it, is we do this. We need to find some coordinates, action angle coordinates for the unperturbed problem. So what I mean now is that these i's, they're going to describe which orbit I'm on, and that those are the action coordinates, and the m is going to tell you where I am on each orbit. So the idea is that we need to find them, and then these i's, they're going to tell us which orbit we're on, so they are preserved under the unperturbed Hamiltonian, and the m is going to tell you where I am on each orbit, and that's going to be, so they're going to evolve with some velocity depending on which orbit we're on. So we need to find these coordinates, and then we write the perturbed problem in action angle coordinates, and you will see here. So then you replace h with with h plus epsilon h1, and yeah, you see that then of course so these disappear. So you just need to. So this is the action of the original Hamiltonian. Maybe I should use this. This is the action of the. This is the original Hamiltonian, and then add epsilon h1 to it. You add this term to the actions coordinates, and this to the angle coordinates. Roughly speaking, you say you don't really care anymore. Oh yeah, this m is going to go from 0 to 2 pi. It's just moving from it's just some parameterization of the orbits. And then I say, okay, I don't really care too much about these coordinates. I want to care. I'm going to approximate. I'm just going to say I'm looking at these coordinates, and I'm taking the averages over each orbit. Now, see, there's the question in chat. Nothing I need to worry about. Yeah. Yeah, that's the next question. Yeah, so we need to choose them. There need to be some parameterization of the, so the I's need to be some parameterization of the set of orbits, and the M is going to tell you where you are on the orbit. And yeah, and then we would like to write it in such a way that I would like to write it in such a way that on these I's I know how to do symplectic integration. So yeah, so this is the this is the averaged mechanics of the I's, and due to the linearity of the bracket, I can move this integral inside, and then you essentially get the average of this perturbation along an orbit. So okay, so these are Kepler. So we're working with Kepler orbits, and I want to work in R3. So these are going to be. Now I've only written that. I've only drawn out the position here, but this is of course it's a system in it's a Hamiltonian system, so it's really evolving in the cotangent bundle. So it's evolving in a 6-dimensional space. But we see as we see here, but it's moving along closed curves. So you have a 6-dimensional manifold that it's moving around in, but each orbit is going to be a 1-dimensional submanifold. So essentially, you have a 5-dimensional set of orbits. To describe both, so you will have one coordinate telling you where you are on the orbit, and then you need 5 more to describe which orbit you're on to get the position in R6, to get the position in T star R3. Okay. So what are these? Action angle variables? Well, the Kepler problem is very well studied, and there are several ones. So they have to, if you recall a bit back, they have to be preserved under the Hamiltonian. We could describe which orbit we're on, so they have to be preserved under the Hamiltonian. And yeah, so these are so they are first integrals of the unperturbed Kepler. And yeah, so this is these are very well studied. The Hamiltonian is preserved. The angular momentum is preserved. And we also have this thing called the Laplace-Runge length vector. And it looks like this. You need to take the angular momentum, you take the cross product with P again, and then you subtract something going in the direction of the origin. No, here this is something I took from Wikipedia, and you see there are some constants here, M and K, that I've just set to 1. And yeah, you see here, and you see this is an illustration of what's going on. You have the P cross L, that's going to point outwards, so to speak, and you have the R hat, so this unit vector in the direction of in the R direction, and you subtract them, and you get this A here. That's going to be the same, and so fundamentally, the A is going to point from the origin in the direction of the periapsis, where the point on the orbit where you're closest to the origin, and its length is going to be it's going to be a function of the eccentricity. Actually, with this simple coordinate, it is actually the norm of A is exactly the eccentricity. So yeah, and but now I said we wanted 5. I said it was a 5-dimensional manifold, but here we have H is a scalar, and these are both 3 vectors with 3 components. And now I have 7. So they are not exactly, so they can't be complete. There have to be some dependencies between it, because now I have 7 coordinates for a 5-dimensional space. And yeah, so that's here. The H is given by the norm of A and L like this, and they have to be always, orthogonal, because the L, the spin, is pointing out of the plane of the vector, while this A is always in the plane of the vector. So they have to be orthogonal. And so I'm going to work with L and these vectors L and A as coordinates, but I have to remind myself that the physical orbits, the ones that actually exist, then L and A have to be orthogonal. Okay, so now I need to figure out the brackets, because I now want to write a Hamiltonian system using the Poisson brackets, and I want to write it in these coordinates. So what happens now? So this is this is the Levi-Civita symbol. So you just compute the brackets. L and L is fine. L and A, they're fine. But if I take the components of A and take the brackets of each other, it's sort of fine. But I get this minus 2h. I get this minus 2h in here. And the Hamiltonian, you can check that's now a Casimir of this bracket. And this other condition that they have to be orthogonal, that's given by C2, which is the inner product of them, and that's another Casimir of this bracket. And I'm making a larger dimensional. I'm using an A and L, so now I have 6-dimensional Poisson manifold. But I get a Casimir, and one level of set of the Casimir is corresponding to the physical orbit. But yeah, this H, of course, the H showing up here is a bit annoying. So there's a trick where you just rescale A, and you divide by. So you need to divide by the square root of minus 2h. If you are in the bound orbit, the Hamiltonian is going to be negative. So as I said before, the norm of A is going to be the eccentricity, so that's less than 1 for bound orbits. So this is fine. I can divide by the square root of minus 2h, and then I get some new. Let's get some new coordinates. These are written as D. I'm not entirely sure why this convention are from, but this is D. Now we see it's a lot easier. We now get just a linear Poisson structure here, and again we have the H is now the Hamiltonian, original Hamiltonian is given by this. That's one, and that's the Casimir, and you also get C2, which is the inner product, which again this tells us which orbits are physical. And then we do another simple change of coordinates. We just do a linear transformation, and we end up with these brackets, and now the Casimirs are given like this. And now we're quite happy, because these brackets here, they are exactly the bracket on R. This is exactly the same as the bracket in R3 with this triple vector product Poisson. So this is the one so the Poisson manifold I have now is simply this 2 copies of R3 with this bracket I already described. So yeah, and you have the Hamiltonian. That's one of the Casimirs. It's given by the sum of the square of the norms, and the other Casimir. Well, the Casimirs are going to be the norms of x and y, and now this is just some other. This is just another way of writing down the same. This is just another way of generating the same Casimirs. And yeah. 2 copies of R3, and the physical relevant ones are going to be and everything is going to move along the surface of spheres, and the physically relevant ones are just the ones where 2 spheres with the same radius. So I could have C2 equals 0, which means that if I go back to the spin and Laplace-Runge length vector, this is just encoding that they are orthogonal. Possibly. Yeah. There is this. If you go into these, if you go into these, like the what do you call them, photographs. So there are some hidden symmetries in there are some hidden symmetries in the Laplace-Runge lens vector in the Kepler problem, and these correspond to rotation in 4 dimensions that I can't read. That I also don't really feel that this is very clear to me. But if you start looking at the orbits of the momentum rather than the position, then you see those are actually tracing out circles, and there is some way of constructing it where you take stereographic projection onto a 4-dimensional sphere, and then you rotate them to yeah. So so if you do it like that, then this would be the Lie Poisson bracket on SO4 star, and that's isomorphic to the couples of SO3. Yeah. So that's the more geometric way of doing it. Okay. So yeah. So and now I should say now I'm happy because now I have this is Poisson manifold, and we can you have symplectic integrators. You have the spherical as Klaus and his collaborators have developed the spherical midpoint method, and you can also do some collective integrators based on the Hopf vibration and so on. So that's so this is this is both the motivation why I thought this is why it works out, and original motivation. This was also I knew about this geometric structure from way back, and I was thinking, okay, how can't that be used somehow? Because now this is it's a Poisson manifold where we know how to do symplectic integration, so can't we apply this to Kepler somehow? So yeah. Okay, so now I can do that, and the next step now is going to be to compute the dynamics, and for that I now need to go. So for that I now need to go back to. So now we have now we know which coordinates I'm going to use for the action variables, and now I need to getting the angle variables and figure out how to do this averaging. And yeah, it's fairly. Okay, I'll skip a bit fastly through this. You have this. I just used the D. The D is the rescaled Laplace-Runge lens vector, so that's going to point in the direction of the periapse. And if I cross it with L, then I'm going to get something that's orthogonal to that. And then it's just some basic trigonometry, and we're using this, and we use Newton's solution to describe this ellipse. Now, of course, this theta here, it is physically an angle. It's not an angle coordinate in the sense of the action angle coordinates, because the motion along this, if you take the time derivative of theta, then it's not going to be constant along everything here. So yeah, there are some. I'll see how much time do I have. It's not. I'll skip a bit. I'll skip a bit through this. It's you need to do some reparameterization in terms of something called the eccentric anomaly, and finally you have something called the mean anomaly given by given by this, and that's actually the angle coordinate, the one I described. This is what is evolving at the constant rate. So this E here, E is given by this, and then you need to do M like this, and that's going to evolve at constant rate throughout the orbit. And yeah, if you want to go back, if you want to go from M to E and over to theta to figure out where we are on the orbit, then so this M is essentially measuring time. And if you want to go back, you need to solve this nonlinear equation here, which is Kepler's equation. But anyway. Yeah. Yep. Yep. Yep.
So which have the rotational invariance built into them.
Yeah.
Right? And also the Hamiltonian must always be preserved.
Yes.
So you're looking at other Hamiltonian systems which have the same standard SO3 symmetry, plus it also must conserve the Kepler Hamiltonian.
Yeah.
So then my question is, but the perturbation. So
yes.
That means there's some constraints on the perturbation because it has to commute with the
well, okay, if we go all the way back, because it doesn't. Because if you go all the way back, let's see, where did I have this? Because if you go, where did I go? Where was it disappears. It disappears in the averaging. Because if you think about what this means, so if you were the H1 originally that doesn't have to commute with the Hamiltonian, but the H bar, the average one, will automatically. Because if you think about what's happening there, if you were to take the replace I here with the original Hamiltonian, then you're measuring the change in the Hamiltonian along you're measuring a change in H1 along an orbit, along a closed orbit of the Kepler problem. Yeah, that's it. The averaging creates the commute, that it commutes. Yes, I was also yeah. So yeah, I was also confused about this from well, wait, why does this always commute, and then you realize it's actually from the averaging. Okay, let's see. So yeah, there's a bunch of you get some nasty integrals trying to solve this. But at the end of the day, let's see, did I write it down here? Yeah, so written in this L and D. Yeah, written in this L and D, the spin and the normalized Laplace Runge-Lenz vector. The perturbed Hamiltonian just looks like this in this for this case. The one the spherical the oblateness correction term to the original Kepler, to the Kepler problem. Then it's just like this. You see it's some Casimir, and then there's something only depending on the spin here actually. So so you could say for this exact perturbation, the dynamics, well, it's still the dynamics are a bit boring. So I'm trying to do this, trying to get some more interesting examples as well, because the method is more general, of course. So yeah, and then you have the dynamics. I've written them here now in this L and D, but I can and then I just do a linear transformation to move it on to the actual SO3 star. And yeah, you see, it's just this is going to be some rotation around the orbital axis of Earth. It's going to tell how the spin evolves, and this is called the precession of the periapsis in astrophysical fields, and it's this formula somehow. Just to get the axis, then I just need to get the dynamics in x and y, which is the ones actually evolving on spheres. I just do something like this, some linear combination. So yeah, now we have the dynamics and symplectic integration on Poisson manifold. I think I've alluded to it. It's somewhat complicated because if you want to have the same If you want to have the same properties as symplectic integrators, to get the symplectic integrator, you need both to have that the optic map is Poisson and it preserves the Casimirs. And you can also say this is 5 minutes. Yeah, it's fine. You can also say they need to preserve each symplectic leaf, and on each and it has to be symplectic integrator on each leaf. So this is one example on R3. So it's first. Oh, sorry. Sort of some comment. No. Okay. So yeah. So you can describe it on the sphere, but you can also that the leaves are going to be spheres. But you can also describe it on all of R3. This is just some term to make sure that both your Zn and Zn plus 1 are on the same sphere. And yeah, so that's how this is the numerical solution. Maybe I'll also again, I'm not so good at graphics, but this is trying to illustrate what's going on. So remember, we kind of lose the information about where we are on the orbit. So rather looking at how the orbit evolves, and this is actually how it will evolve. And I can't remember the time scales. This would be some orbit in a low Earth orbit on a inclined and highly eccentric orbit, and this perturbation here I think is over a couple of decades. So it is fairly slow these things, but I haven't tried testing it up with actual data to see how well this matches up yet. But these kind of things happen. But yeah, if I'm capturing this should capture the interesting. This should capture the main term with this spherical oblateness correction. But yeah, yeah. So the orbital. Let's see. So then I need to remember Yeah. So it's going to be, it's in the natural time scale, it's around 100, and the natural time scale is such that 2 pi is like the shortest possible orbit around Earth. So 2 pi is like 80 minutes, and then this would be this is around 100, so that's 15. Yeah. So this is decades, and I think the orbital period here is like hours. Now this is getting in my way. How can I? That was a problem. Okay, so let's go here. So yeah, these are just the plots of the numerical solution, and yeah, the video is perhaps even better. And yeah, this is just another way. This is how the spin is just going to move like this, and this precession of the periapse is what you really saw what's going on, being quite wild in the animation. It's moving around the Earth in some mysterious some pattern. Kind of reminds me of heavy top in some way. But yeah, and yeah, the order is it's a second order integrator as expected. I've also done some collective integrators, getting and then at least fourth orders that also works. So yeah, and yeah, the invariant, of course, the original Hamiltonian, that's just staying on the sphere, that's perfectly preserved, and the H1, which is this perturbation term, you expect it to be change. You expect it to change, well, like this, and some periodically, and we see that. So that's it. Thank you for your attention.